The next speaker is Libb Thims, Institute of Human Thermodynamics, USA. The title of his talk is A Theoretical Torricelli Social Barometer to Measure Social Pressure. Professor Thims.
All right, can everybody see my screen share?
Yes.
Today's talk is going to be on a theoretical Torricelli style social barometer to measure social pressure. So this talk originated from my draft manual, Human Chemical Thermodynamics. And this book I've been working on, finished up the history of thermodynamics up through from the ancient Greek denial of the void by Parmenides up through the development of the steam engine by Watt. So what we're going to be doing in this, what I'll be presenting in this talk is a theoretical Torricelli style barometer that can be moved into and out of social systems to measure social pressure. And the talk comes from the highlighted sections of my manuscript. The PDF is linked in the chat session, particularly between 1639 or 1632 when Galileo started to probe the vacuum question, all the way up to Boyle's spring of the air in 1660. There were over 100 experiments done on the vacuum. And this was before there were no equations. This is pre-thermodynamics. And if you had Boyle's law, for example, that pressure is inversely proportional to volume, wasn't stated as an equation, it was stated verbally. So the theme of this talk is to get back to before thermodynamics, temperature, pressure, volume were all measured, there was debates on how how you could theoretically develop instruments to measure these variables. And right now in thermodynamics applied sociology, we don't have instruments. And the link I've linked to at the bottom called Human Thermodynamic Instruments kind of gives a history of attempts to develop instruments to measure temperature, pressure, volume, or entropy. So here we have a basic Torricelli barometer. And it's going, if you take this and you move it into, say, a village, a town, or a city, you will not see a change in the pressure. You will see atmospheric pressure. Now here we have our basic social system. An inexact differential of heat, dq, goes into the social system, which has an exact differential of internal energy, U, and it produces a differential change in volume, pushing the boundary of the system outward, which produces the system does an inexact differential of work on the surroundings. So if we look closer at this system, we will have an internal pressure inside of the system, and we will have an external pressure in the surroundings. And right now, there's no way to measure this pressure as we understand as scientifically. So here is the Watt Southern Indicator diagram on the left. And this is where we get our first pressure, temperature, volume diagrams, which is kind of the symbol, the core symbol of engineering. On the part C right here is the Watt pressure spring measured pressure measuring device. At the bottom here, E, we have the steam pressure inside of the cylinder, and it pushes on this piston here and pushes up on the spring, and this pencil goes up and down, and that gives our pressure measure on the vertical axis. And there is a string attached to this board which slides sideways that attaches to the piston. So the string F, the cord F here, attaches to the rod of the piston by the string here and goes back and forth. And this gives us a reading of we are able to measure the work, which is the volume inside of the area of the curve. So here we have Clapeyron in 1834 took the work of Carnot, and he made the first pressure volume diagram here. And one thing that's interesting here, we have these diagrams came from a mathematician named Davies Gilbert, who used Newton's method of fluxions and fluents, the first form of calculus, in court to prove that John Sotherby's steam engine was more efficient than Watt's steam engine. So Watt heard about this, and he assigned his apprentice John Southern to make these indicator diagrams. So here we have this was what is called here the Pfaffian form, inexact differential of work times the pressure times the exact differential of the volume change gives us the area under the curve, which is the measure of the work of the solar system. And later Clausius and Thomson copied all this or duplicated and came up with a formula for entropy. So what we'll talk about today is a way to measure pressure. Now, pressure came when in 1630, Giovanni Bellini approached Galileo, and he said that he had this problem on how siphon pumps could not measure, stopped working at 30 feet. So here we have from the 15th century, we have a miner pumping up and down to get water out of a flooded mine. And Galileo thought about this problem, and the question at the time was that whether or not the suction pump stopped working because of the vacuum, that there was a vacuum created that stopped the pump from working. And Galileo didn't necessarily believe in that, but he imagined that the column of water was similar to a long column of rope, that once the water reached 30 feet, the bonds in the water would break, and that's why the suction pump stopped working. So he imagined water to be a wood or stone column like this, and if you put enough weight on it, for example, block C here, the column of stone would break, just as the column of water would break, just as the rope would break. And he wrote this in his 1632 dialogue concerning the two new sciences. And when this book was published in 1638 in Rome, Gasparo Berti took this idea of a long 30-foot column of water breaking, and he built it. He made this device on the side of his house, which is about a 35-foot copper tube with a glass bulb on the top. So he filled this whole tube with water, and he wanted to see. He put a tub underneath it at the bottom, and there was a valve at the bottom which he closed, and there's a valve at the top which he filled the whole column completely filled with water. And then he opened the bottom valve, and he wanted to see if this water column would break. And what he found was that the water descended only down to this point L here, or to about 27 feet. And at the top of this was supposedly, according to Berti, who believed in the vacuum, the world's first vacuum. And this stimulated a large amount of debate throughout Rome, France, and eventually England. And they put another number of things. Over 100 tests were done inside of the vacuum. For example, putting a bell, we see here inside of the vacuum, putting birds in the vacuum, putting dropping objects in the vacuum. Now, in respect to the next step was Galileo students Evangelista Torricelli and Vincenzo Bellini gleaned on the idea that they could use mercury, which is 15 to 16 times denser than water, and make a smaller version of this 30-foot water column vacuum device. So Torricelli had Vivani take a column of mercury and invert it into another tub of mercury. And of course, the mercury fell, and at the top we have what's called the Torricellian space, or the vacuum. And Torricelli's genius was that he believed that the reason that the mercury column stopped at a certain height was that the 62-mile column of air above the surface of the Earth, shown here, was pushing downward on the surface of the mercury, and the pressure of the mercury was balanced by the pressure of the air, or the atmospheric pressure, and what was left at the top was the measure of the atmospheric pressure. So in 1648, Blaise Pascal learned about these experiments done by Torricelli, and he did an experiment where he took Torricelli's mercury column barometer, the height of which measures according to Torricelli, the pressure of the atmosphere, and he had his brother-in-law climb to the top of Puy de Dome in France, which is a 4,800 foot mountain. And he found, as he predicted, that as his brother-in-law climbed the mountain, the pressure would fall. So we see B here is the vacuum increases, or the height of the mercury decreases, and this gives an indication that there's lower atmospheric pressure at the top of the mountain as compared to the bottom of the mountain, where the column is taller and the section A of the vacuum is smaller. So how we can understand this is in terms of Newton's law of gravitation, where M2 is the mass of the Earth, and M1 is either the mass of the mercury or the mass of the air molecules of the atmosphere, which are N2 and O2 predominantly. So each one of these masses attracts with a force towards the Earth, and whether there'll be a force pulling the mercury towards the Earth, or there'll be a force pulling the N2 and O2 molecules towards the Earth, and there'll be a U-shaped balancing of pressure here. And the force divided by area equals the pressure. It was as proved by a formula introduced by Daniel Bernoulli in his 1738 Hydrodynamica. So how this applies to social forces. If anybody saw my talk yesterday, I talked about the Princeton School of Social Physics. So one of the students of this school was geographer William Warnitz, and he made these social gravitation models where he took, here's a picture of him right here building this. He took pins and he measured the population at different zip codes throughout the United States, or different area codes, and calculated he measured things such as the rate of exchange of letters between different populations, and telephone calls going back between different populations. And so he built what is called the social gravitation model, where the P1 and P2 are population potentials. For example, the population of New York versus the population of Chicago. D is the distance between two cities. K is a constant, and force is the force of attraction between, say, New York and Chicago. New York, in this case, shown here being the sun, Chicago being a planet that rotates around New York. So in our model here, the New York would be considered in terms of the mountain here, New York would be considered the Earth, and the farther away you get from the Earth, you would be at the top of the mountain. There would be a lower social gravitation pressure according to this, the equation.
Excuse me, 5 minutes left.
5 minutes, okay.
Yes.
So from this is a bit theoretical, but I glean the idea that Torricelli's barometer can be inverted into the effect of making a social experiment in the form of a double-decker bus, where the mercury would be one human species, and here's an example of and the outside air would be another species. For example, this is a bus shown here of people in Hong Kong, and population is very dense there, so it's similar to a city like New York. And the proposal is that if you did something sort of a social experiment where you had a bus with, say, a certain group of, say you took 10 college students, and you did a double-blind placebo-controlled experiment where you told them they're going to drive into different cities, for example, New York, or small cities, or countries, and told them we're going to film you, and we're going to watch your job is just to have a good time or something like that, kind of like the MTV's show The Real World. So the prediction would be that at the top of the bus, there would be an empty social space, which would be equivalent to the social vacuum, akin to the Torricelli vacuum at the top of the mercury column. So if you drove this bus into a city like New York, or say they were English-speaking people, and drove them into, say, Hong Kong, in a city where no one spoke English, there would be the mercury-like social species wouldn't mix very well with the Chinese speaking social species, so there would be a sort of social vacuum, and this would be a way to measure social pressure. And here we see an example of high school social pressure, and so the prediction would be that the closer you were to a large city, the social vacuum would be smaller, and you would have a higher social pressure, which would be measured by the height of the mercury social species in the double-decker bus or RV. And if you were in a small town, the social vacuum would be larger. So to conclude, here we have we wouldn't be able to measure the pressure inside of a pressurized city. There would be a smaller social vacuum, and in a more dispersed area, there would be a large vacuum. And if you get to the point, for example, the movie Into the Wild, which is based on a true story where Chris McCandless completely detaches from society and goes to Alaska where he has no social interaction. You see him sitting on top of the bus where the Torricelli, the bus is completely empty, which means there's a social vacuum inside of the bus, there's no pressure. And so here we see the last slide this comes from a famous experiment called the vacuum within a vacuum. So if you take a mercury barometer and you put it inside the vacuum of another mercury barometer, the height of the mercury column would go down to the level of the mercury in the dish. And this is what Robert Boyle found when he did this experiment. Just like the height of the social vacuum goes down to zero when a person goes into the Alaska wilderness. Does anybody have any questions?
Yes, thank you for very interesting drawing of this picture. We still have a society in economics started with Samuelson and his student on measurement and the importance of measurements. Now, in the same way that Bernard was talking about how prediction would affect the final outcome, do you see that measurement has this effect when it comes to social sciences, that it actually affects whatever the subject was that we were aiming to measure. Any reflections on when we go from natural to social, that would be great.
Well, I guess I don't really, basically, you have to measure everything in the social sphere in terms of SI units. So we have to measure pressure in newtons per meter area. And that doesn't matter if you're measuring pressure in the ocean, pressure in the atmosphere, or pressure in New York. So you have to be able to measure social pressure in terms of force of people in a society pushing on a person or economic system per unit area per surface. And so that pressure is the simplest one. The temperature gets more complicated when you're talking about movements of people, in the same way with energy and entropy, and they all have to be measured in SI units. Does that loosely answer your question? I didn't catch the full question, but
I'm wondering if the act of measurement has an important effect when we bring our frameworks of measuring in relationships from the natural sciences to social science.
Are you talking about something like Heisenberg uncertainty principle?
That would be part of it, but in general, I feel that in economics, we take so much pride in just measuring whatever we call a proxy for the actual element that we were interested in, because it is not so cut and dry as the natural sciences. We always have to define a proxy and then give it a definition, which is not hard. And then that measurement does not necessarily represent what we were meaning to discuss, unless we limit it by definitions. And therefore the human effect, so to say, comes into picture and introduces some nuisance in the transition of the beauty of what measurement can allow in natural sciences when extended to social.
Yeah.
What the other speaker is now available apparently, so we have to accommodate him.
Of course.
My apologies for interrupting.